We're on the air. Excellent. We are on air. Start screenshot. Beautiful. So that's working. Just going to make that smaller. And document camera is not connected. Okay. So I'm beginning to think that this cable is broken, but oh well. So no writing. Exit, yeah, exit. Reluctantly, I'll exit. So we have to do one more little piece of knowledge, which is finishing up symbol tables. So last time, I told you about this red black tree that's built into Java. Its name is java.util.treemap. So anyone can use it, and it is already there. So why do we have to know how to implement binary search trees? Why are you going to spend the whole of next year, or the first 3 months of next year, relearning how to build binary search trees and red black trees and skip lists and hash tables and what other cool sounding data structures can I think of now? Well, why do you need to learn that? Well, I told you before that sometimes you want something special out of a data structure. It needs to behave in a way that's slightly different. So we need to know how to make our own data types. We may want to adjust the data type to behave, to make it easier to use in the rest of the big application. We may want to experiment with data types. You want to make a new kind of data type that hasn't been thought of before, and then you take an existing one and you modify it. So it's important to know how that works. If you're working for a company, you may want to use a data type that was written by someone else, but you don't trust the code, so you want to rewrite the code. That's actually a bad thing. It's called the not invented here syndrome, NIH. And it causes companies to spend a lot of time reinventing stuff, reinventing the wheel. So rewriting binary search trees, although there are already perfectly good libraries available. Programmers tend to suffer from that. It's a bad thing on the one hand because it wastes a company's resources. On the other hand, it's a good thing for learning because you're learning how to implement a red-black tree or what have you. And that's the most valuable kind of learning. You can close the floor. If you want to learn how to program something, you have to do it yourself. You have to write the physical code. Just looking at someone else's code is not going to help much, even though reading code is a good thing. You may use someone else's library, not use someone else's library, because it has some kind of license attached. So many companies want to use software that exists, libraries that exist, but those libraries are open sourced, and those licenses specify that if you use this code, your source code must also be open sourced. You can imagine that a company they do not want to give away their source code, so they may not be able to use kind of library. All kinds of issues. There are conferences on licensing of software. I've been to them. It's really exciting. Okie dokie. Right, all that to say that we're going to use TreeMap, which is Java's built-in version of red black trees. It's also a symbol table. It has the same operations, and more, in fact. It also has a get, which we're calling right here. It has a remove, which we're calling right here. Its version of contains is called contains key. So our symbol table needs a routine called contains. I give it a key, and it tells me if the symbol table contains a mapping for this particular key. And we call the tree maps, which we've called st, that's a local variable, or instance variable. We call st's contains key routine. And the red black trees that Java implements also has a contains value. So you can also look for values. And then it has a special routine, there's something called iterator. We haven't talked about that, and we may soon. Symbol tables, iteration. What is this iteration story? Well, we've talked about it. If we have a binary search tree, there are various ways we can list all the nodes in that tree. We can walk through the tree and display all the nodes, or walk through the tree and add up all the values in the tree, or walk through the tree and just make a recording of the values that's in the tree. We won't walk through the tree and search for a particular key. That's not something we do. we'd be walking through a part of the tree, because if we're looking for go and the root key is high, then I know that I don't have to even search the right-hand side of high. Go cannot possibly be there, because the right subtree of high only contains nodes whose value is greater than go, or sorry, greater than high, and go is less than high. If go is anywhere in this tree, it must be in the left subtree. So then I'm at the node at. If go is anywhere in this subtree, it must be in the right subtree, because go is greater than at. 2, it must be in the right subtree R. There we find go. So when we search for a key, we are only going to walk through a part of the whole tree. But if we want to do something to every single node, we are going to, it's called traversal. We're going to traverse the whole tree. There are 3 ways of doing this, and we've looked at this. There's something called in-order traversal, where I'm at a node, I need to traverse the whole tree. So I say, traverse the left subtree first, so the whole left subtree. Then I do something to high, like print it. And then I do something to the right subtree. I traverse the right subtree recursively. We'll be using recursion for all of this. What will happen if I do in-order traversal, printing all the nodes in this tree? Well, let's think about it. First, it'll print all the nodes that are smaller than high, then high, and then all the nodes, all the values that are greater than high. And the same for the left subtree and the right subtree. So I'll get an alphabetical listing, in this case, in order sorted listing of, or printout at least, of all the keys in the tree, all the values stored in the tree. So these in-order traversals are really useful. I mean, it makes sense to use them, and we do all the time. Sometimes I don't really care about the ordering of the nodes, and then you don't really care which traversal you use. But this is in order. Then we have, no, nobody wants to ask anything? No? Okay. Then we have pre-order traversal. So first I'm going to do the high, then the left subtree, then the right subtree. We've looked at this code as well. Let's just look at this particular piece of code. If x is null, if this is the empty tree, there's nothing to traverse, so I don't do anything. Then I print out the current key, then the left, and then the right, recursively. I'm recursively calling pre-order. So whatever I do to the key is done first before I do, it's pre the left and the right subtrees. Why do you want to do this? Why do we want to do this? Well, it's not perfectly clear why we want this, but post order, I can explain to you quite easily. So we have already had to use trees to do the first project about Art Explorer. And there, we should have used, and I'm pretty sure we did use post-order traversal to evaluate the expressions. I'm at some kind of expression. I first evaluate its left-hand side, its left-hand operand, its first operand, and then its right-hand operand. And after I've done that, I perform the operation. So this recursive post-order call could be something like to evaluate the subtree. And it may send back, let's say it sends back a value. In this case, it's void, but it may send back value. And then I get a value back from the right subtree. And then lastly, the last step, instead of printing, I'll combine those two values. So that I'll check what kind of operator is stored to this node. And if it's a plus, I'd add the values and send back that value. Or it's a minus, I'd subtract the two values, left and right, and send back that value. So it makes a lot of sense to do post-order traversal. Post-order traversal happens every single day. In fact, every single time you compile your program, Java is post-order traversing a subtree to that represents your program to generate the bytecode instructions. Java bytecode instructions are generated in post-order order because that's how machines like to evaluate expressions. I first want to do the one side, then the other side, and then the last operation. And in the same program, in the compiler, Java also uses pre-order to do certain things with your program. They're a little technical to explain, but it's important for the compilation of your programs to also do pre-order traversal of your whole, of a big tree that represents your entire program. So that's what Java is doing. Okay, a few more things. This is basically cleaning up. I mean, this end of this chapter is collecting a lot of stuff that we've actually already talked about. We've talked about this enhanced for loop. Sometimes it's called a for each loop. Because instead of having to write for initialize a variable, condition that will terminate the for loop, and the increment step, so instead of having those 3 steps inside of the for loop, I can just write this. I can write st is some kind of symbol table, and in this case, it maps strings to integers. So it's a container of values. It contains many, many values, many, many mappings. This depends on the container itself and how it's implemented. But in the case of st, it's actually something that is iterable. I can iterate over st, over all the values in st. I want to say I'll traverse the values in st, but we usually use traverse for trees. If st is implemented as a linked list, we don't usually say I'm traversing the linked list. I guess you may say that. But st may be a linked list, where each node stores one mapping. And then the iterator will simply walk down that linked list. And for each element, in the case of st, for each key that is mapped to something else, it'll execute the body of the for loop once. So we start by declaring a local variable, string s, which will hold the current value of the key. We want to iterate over st, so over all the mappings. And then for each of those mappings, s is going to have the value of the key, and this is going to print out get s plus s. This looks complicated. What does it do? Oh, tricky. What's your name? Yes, yours. Andrew. I've never seen you before, Andrew. Are you doing computer science? I'm kidding, I have seen you before. What I don't understand, what's going to be printed here? You can't read the screen? That's a bit of an issue. You can't read the screen. That's a big problem, Andrew. How do you follow anything in class? You watch it on YouTube, don't you? No. Oh, you just listen. It's just like an audio book. It's like I'm narrating a very boring book about programming. Okay, Andrew, I've removed your excuse. I've enlarged the font. Oh, but you may not have heard what I said. So let's see. This is an enhanced for loop. Sometimes we call it for each loop. st is a symbol table that we've implemented. And in just the next slide, we'll get to how to make st iterable. But the bottom line is it means that I can walk over all the mappings in st. So this for loop is saying, make a local variable s that for each of the keys in st, execute the following piece of code. And I want to know what is being printed, Andrew.
Just each string and then just a space and it's integer. I mean, we give the integer first and then space.
Okay. For a second, I thought you were going off the rails. I just picked the one student who had not learned anything in this course. But you predicted, and eventually it came out fine. So this is the mapping that S is mapping to. Sorry, this is the value that S is mapped to. Yes? Andrew? I need you to confirm my... Okay. And as you said, it's an integer, because st maps strings to integers. So this is the value that S maps to, and then it prints a space, and then it prints a key. So if this were a telephone directory, it would be printing the telephone number and a space and then the name. Do you agree? Okay, excellent. And if you can't see the screen, you must really not sit at the back or watch the YouTube videos closely, because I think there's a lot of info on the screen that you're missing out on. It's also almost impossible to imagine how anyone can survive this course by just listening to me. Okay, but I'm now going to turn the screen back down. Okay, good. I'm just warning you. Oh, great! Now I've broken something. Good, excellent. Okay, now I'm going to turn it back up, Andrew, because you can't see and no one else in class can see either. We're going to zoom in. Now it's tricky because if you're like me, you don't like zooming in because you're missing context. But we'll start here. I've just told you all this big story about how you can iterate over certain data types. This is not true for all data types. You can't iterate over an array. Well, actually, you can iterate over an array. That's a big fat lie. You can't necessarily iterate over, let's say, your own data type. In fact, we've done this. We've defined symbol tables using arrays. At least we've talked about that. And in those implementations, we didn't write the code that allows users to iterate over that symbol table. So this is code that you or whoever writes a data type need to add to the data type source code to be able to use it in a for each loop. I think I'd better fire up the old Eclipse because I want to do a little demo thingamajig in a second. While that starts up. So what code do you have to write to be able to use a data structure in a for each loop, in a for each for loop? Well, firstly, here we go. Public class BST, that's binary search tree, and it's a parameterized class. So it takes two parameters. One is the key data type, and one is the value data type. And we write it like this. These are kind of the angled brackets that specifies the parameters of this data type. And we don't want any kind of key. We want a key that we want to have keys that we can actually compare to each other. So I'll be inserting keys into the data type, and those keys will be compared against each other. So I can keep, let's say, ordered array. So these keys need to be comparable. So I say that it extends a comparable key, which means that this key is some kind of data type, and I can compare this key by calling compare to other keys. Okay, that all makes sense. And then we need to add this new part. It implements iterable key. So it implements another data type, actually an interface, that's also parameterized. This means that I can use this BST in a for each loop, and it'll return keys. Now, key is a parameter of the public class, so it's not one specific thing. If I make a BST that maps strings to integers, it'll implement iterable string, because the key is string, and I can iterate over strings on a BST. If I use BST and I give it the parameters integer double, I'll be able to iterate over integers. Okay, we'll see this in a second. I hope it's not too confusing. If you find that confusing, you should have a little look at this routine. So here is a routine. Now it sends back something called an iterator. This is something different. Here at the top, we said this is an iterable. This is a data type that's iterable. And the requirement for being iterable is that you must have one routine called iterator. And it must send back a big I iterator of key type. If I wanted to iterate over the values in this BST, I would have said it implements iterable value, and here I would have had to say iterator returns an big I iterator over values. We'll look at code soon, so that's fine. And now things become a little complex. So what does this iterator routine do? It needs to return an iterator, but it's going to declare an iterator right inside this class. So it's going to be an inner class, a nested class. We've seen that before with Node, for example. That class is going to be called inOrder. And it is going to implement iterator. It's going to be an iterator over keys. And this small I iterator routine of mine is going to create a new instance of class inOrder, and it's going to send that back. Now I really, really wish I could use the little document camera. Okay. So this code is not difficult, but it's tricky. When I have to write an iterator, I open up some of my old source code and I just copy it over. Because they're almost always the same. There's perhaps one or two small pieces that change, but almost always these iterators are identical. So it needs to have a constructor. It needs to have a routine called hasNext to be an iterator. And it needs to have a routine called next. And these routines have specified, it also needs to have something called remove. So these routines have specified meanings. Remove is supposed to, if you're iterating over a lot of, let's say, keys, and you call remove on that key, you're supposed to be able to delete that key from the symbol table. But for many data structures, this is impossible. You can't just delete nodes as you're walking through the tree, or you can't delete nodes as you're walking down a linked list necessarily. So many data structures, many containers, so even in the Java libraries themselves, do not support remove. And they just throw an exception. It says unsupported operation exception. hasNext is supposed to send back whether or not there is a next element that you still have to visit. And next must send back that next element. Must go to the next element and send it back. So this stuff won't be in the test. But it's important to understand how it works, because it's important to understand how any code works. If we have code we don't understand, that means we're still not good programmers. And the whole idea of doing Computer Science 1 is to get our programming skills up to, well, as high as we can. So we must never have code that we don't understand and just ignore it. If I read this code and I couldn't figure out what was going on, I'd do one important thing first, and that is to format it properly. Because at the moment, this looks terrible. I mean, all the routines are listed beneath each other. I can't clearly see the separation, and I don't like it when I can't see things aren't clearly separated. So what I'm going to do is I'm going to make this smaller again, and then we are going to write our own. Okay, that's for next year. Let's just go there. We're going to write our own copy of this, of an iterator. And we're not going to use a binary search tree because there is that example on the slides. We're going to use an array. We're going to iterate over an array. So a quick little bit of source code. And then we'll stop. So all I have to do is write a small program and then I have to stop. just like the chats. I don't really understand why the chats take so long, because you just have to write a whole program and then go home, and it sounds so easy to me. But I realize it's much more difficult if you sit there and you don't really know what's going on. I don't know what it is. Okay, rightio. So we're gonna make a new project. I'm gonna call it. Yes. What do you want? What do you want me to call it? It will definitely be up before that's tomorrow. I'll try to put them out tonight. It's just tricky to sort out who's been ill and who's not been ill, but I'll put them up tonight. Okay, they're just a random selection, but you're right. I must put them up. Let's just call this. What should we call it? Come on, you asked a totally relevant question. What shall I call it?
It's called project name.
No. Oh. It's going to be about iterator. What's iterator in Afrikaans? Itereer. Oh, that's ugly. So I'll just call it. I'll just call it quiterator. Just because it's a funny word. That's because I want to. I can do what I want. Quiterator is my package. I always like doing that. Okay, now I'm going to stop using quiterator because I want to implement some kind of container. It's just going to contain integers, but I'm going to make it generic. But let's start with integers, and I'll make it generic in a second. I'll add parameters to it in a second. So it's going to be an integer set, and therefore I'm going to call it int set. It's not even going to be a set. It may just be a store. But I'm calling it int set, and it's internally going to use an array of integers. So that when I construct it, when I write the constructor, I have to tell it how big to make this int set. So I'm going to make it and I have to keep how many values are stored here. So, oh, my mistake here. Thanks, Java. I'm going to say at the moment it's empty. Okay. Andrew, can you see? Nothing. Okay, that's fine. But I don't know what I'm not going to say. I'm not going to read the code, so you'll survive. Okay, excellent. Okay, right. I want a routine to add a new value to the set. So I have to write add. And this is going to be quick and dirty. So it's not going to complain about the set being full and all that. It's going to add something if there's room, and if there's not, it's going to not do anything. So if the size is less than the space, I'm going to say put the new value at the end of the array, well, the end of the part we're using, and just increment the size. Cool, right? And I'm going to write a routine that just checks if a certain value is in the set. So public void, no, public boolean contains int value, and it's going to say start I at I. While it's less than size, increment. If the ith value is the one I'm looking for, then return true immediately. You can just stop there, right there, and return true. Otherwise, return false. Everybody happy? Okay, you have to be happy quickly. We don't have much there. But a moment ago, I slipped up, and I revealed, unwisely, that we can even iterate over arrows. Did you hear that? Okay. So why don't we do that right now? Instead of having to say for int I, I'm using the old style for loop, I could just use a new kind of for loop. Well, I can just say int I, in v, in values. If v is the value I'm looking for, return true. This is my old code that I've highlighted, and above it is the new code. It uses that new fancy for each for loop. Everybody happy? Andrew, are you happy? Your happiness is paramount to me today. I have a small issue here. I have a small problem. Which values exactly will be iterated over? It will be all of the values in values, won't it? It's going to go start at the first value of the array, and it's going to look at each of them right to the end. Even if size is, let's say, 0, if there are supposedly no value stored in the values array, it's still going to check each of them. And the way Java works is that if I allocate a new integer array, its size is, I have to give the size, but the content is initially 0 for an int array. So there'll all be a lot of 0 values. Even though the array is empty, I'm thinking that there are max copies of 0 in the array. So unfortunately, in this one case, this won't work. We can't really write that. This will look at all the v values in all the ints in values, and we really only want to look at the first size integers and values. So I have to write old style for loop. Okay, and now I want to write a routine that will iterate over the values in values. So I want to be able to write a routine like this. This class is called intset. Let's say I want to store 10. And then I'm going to write add 3, 1, 4, 1. Print, I'm just going to use the standard Java way of printing. Is contains 5. That'll probably be false. Is contains 4. That should be true. Okay, so my main routine makes a new is, a new int set called is. It adds 3, 1, 4, 1. And then it checks if it contains 5 and 4. So that should print false and true. Let's see if we can run this. Right click, run as. Okay, and something printed on the console. Hang on. Oh, excellent. That's exactly what we expected. Is contains false, 5. That's false. Is contains 4. That's true. Excellent. Now I want to print out all the values in the int set. So I'm going to add a little routine here, and I'm going to use my new special for loop. So I'm going to say for each values in is, sys out. Okay. I'm just going to print b. Okay. So I want to write a smart new for loop like this. But Java's complaining, or rather Eclipse is complaining, Java's also complaining, the Java compiler is not compiling, so Eclipse is telling me that can only iterate over an array or an instance of Java lang iterable. It's telling me that is, this int set, is not an iterable. I haven't written the code to make is iterable. So I have to add that code. I must say, is implements iterable. And it's going to iterate over ints. But unfortunately, we've already know that when you add a type to a data type, it's a parameter to a data type, it must be some kind of object. So int is not an object, it's a built-in primitive type. I'll have to use the object equivalent, which is big I integer. Okay. Oh, now there's some other mistake. Is this thing never satisfied? What's wrong now? The type inset must implement the inherited abstract methods, iterable, blah, 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 iterator. Ah, okay. So if I want to implement an iterable, I must implement this routine called iterator. Just add it, please. Okay, now right at the bottom, you just put my iterator, but I'm going to move it up a little bit. There we go. So it's a routine called iterator, which is behind the scenes is called by the smart new for loop, the for each loop. It'll call the iterator routine in my inset, and that'll send back an iterator, big I, over integers. This is something that has those three routines, has next, remove, and next. Okay, and I'm going to do the same as on the slides. I'm going to say return, now I've got to know what to call it. I'm going to make a new class that will just step over the array. So I'm going to call it stepper. It's a new stepper. Okay, and Java's complaining because it doesn't know what a new stepper is, but I'm going to tell it right now. This is a private class, stepper, that I'm defining here inside inset. Because no one else outside of inset needs to know how a stepper works. It's only inset that will be using the stepper. So I'm going to say it's a new stepper, and it's going to be a kind of iterator over integers. And if it's an iterator, it needs to implement certain methods. It needs to implement has next. There is a next integer to iterate over in my inset. It has to implement next, which actually sends back that integer, which is why the return type is big integer. And it has to implement remove. Well, remove is almost the easiest because we almost never implement that. So I'm going to say throw a new except unsupported operation, I think it's called. Unsupported. Excellent. So remove is not going to be implemented. Sometimes you do want to implement remove, but oftentimes you don't. Okay? And how is the stepper going to keep track of which integer to return next? I'm going to give it a private local variable or private class variable, private int index. And it's going to start at 0. And then I'm going to say, I'm at some index. There is a next element to go to if this index has not reached size. So here I'm going to say, return that index is still less than size. So index is going to start at 0 when I start stepping. It's going to be incremented each time until it reaches size, and then I can't iterate any further. Okay, and now for next, I'm going to say, I kind of want to say return the values at index. But I'm a little scared. I mean, something may go wrong here. Who shall be a victim? What's your name? Right in the back, right in the corner. I know you. I'm sorry to disturb your cell phone game, but I'm afraid you haven't even been paying attention, so you can't answer my really intelligent, stimulating question. But I've got a funny feeling that this is not going to work. What is going to go wrong?
An error.
0 marks in the exam. No, an error is not going to go wrong, man. It doesn't gel. I don't know. What is the problem? Okay, excellent. That is the right answer. If you don't know something in an exam, please don't make something up. This is wasting my time. It's very wrong. Okay. My issue is that, okay, this is fine and dandy. So index starts at 0. When I'm asked to give the next integer, I give back the one at index. But if I'm asked to give the next integer after that, I'll be giving the same values at index. And it'll always be index equal to 0. So I'll be returning value 0, values 0, values 0, all the, I'm not incrementing index as I think I should. So I'm going to say index plus plus. So first I find the value in the array. It's stored at index. Oh, these are such bad names. Values is values, and index is an index. Okay, we'll just have to change some of these names. Okay, I'm going to immediately change values. I'm going to call values. And index, I'm going to call gindex. Okay, just so I can speak more clearly. So when routine next is called, it finds the value that it's stored at index gindex in the array values, okay? And then it also increments gindex because the index is now moved on. Okay. And that'll be fine, I think. So have we done all we should? This is stepper, it's an iterator. It needs to implement these 3 routines. It keeps track of which index to send back next by using this variable gindex. And has next says that our gindex is still less than size. Next says find the value at index gindex in array values and also increment gindex, and remove is unsupported. So that's fine for stepper. When this iterator small I routine is called, it creates a new stepper which it will send back. Someone wants to iterate over the array and it says, I'll make you a stepper. It creates setup stepper and it sends back that stepper, which means that 2 different routines can call iterator after each other and they'll get 2 separate steppers. One for the first caller and I'll create a new one for the second caller. So they can iterate over values independently, over the inset independently. We'll see that in a second. Okay, so that's a routine iterator, and I had to add that so that inset can implement iterable. And so finally, there's no more errors down here. I can have a for loop that walks over my inset. And oh, why is there still an error? No, there's not. Oh, right. So I can execute again. I'm going to make the screen a little bigger because it's so dramatic. Run inset. Oh, excellent. So it prints out 3141. Okay, I know you do not have any time to do this, but sometimes it's interesting to experiment with code and to see what happens if you break it a little bit. Let's break this a little bit so that it doesn't stop at size. It actually stops at the length of the array values. Sorry, I couldn't. Values. So it doesn't stop at size. It doesn't respect the size, number of elements actually stored there. It just goes all the way to values. If I run now, oh, look what it does. 3141 0 0 0 0 0 0. So it actually printed all those zeros as well. And one last trick. As I said, every time we call iterator, it makes a new iterator, makes a new stepper, and sends that back to us. So I can have more than one iterator over this inset. I just want to fix this. We can do this. We can say, this is a for loop, and inside it, there's going to be a second for loop over the same inset. And what it's going to do is it's going to print It's going to print V plus W like that. So, and then at the end of each line, it's going to do a system print line. Okay, right. It's going to be excellent. Just want to add a little space there. So look, it has printed me a matrix of all the combinations of values in the int set. And I could do this easily by just adding another special for loop inside the previous for loop. Okay, I'm going to stop now. I'm not going to do any new work on Friday, but I will be here to answer any kind of strange question you might have. Do you have questions about the test that you want to ask now? No? Okay. Yes, you do.
Which chapters will be covered exactly from?
Were you in class on Monday?
Oh, yeah.
Well, I'm not saying it's a bad question to ask which chapters will be covered. I just want to ask you if you remember what I said on Monday.
Yeah, you explicitly say you just mentioned some topics.
Well, what specifically? What did I say?
You said questions from the chat, then
No, I mean word for word.
can't get directly.
Well, I can just play you a YouTube video. Okay, please go to YouTube and watch Monday's lecture again. That'll increase the views. And as you know, in the future, I'll be paid by the number of views I get on YouTube. I can't wait to get 1 million views because I'm going to be so rich. No, on Monday, I explained exactly how many questions there will be in the test and what each question will be about, roughly. Okay, so I'm not going to repeat it. You can now watch the YouTube. Well, ask your question. Let's see. Perhaps I want to repeat what you want to ask. You wanted to repeat his question and then force me to repeat my repetition?
You said that the first question was going to be like the last test.
Yes.
3 questions on encapsulation or something.
Yes, anything we've done in class.
Will they be-
So that's fair. I mean, that's a sensible question to ask. What does the first question cover? Right. Oh, that's what you meant. I'm sorry, I couldn't deduce it from your brief question. The first question will cover chapters, sections 4.1, 4.2, 4.3, 4.4. So everything we've done in the second semester. Is that accurate? Yes. So if we've done anything in the second semester, I won't ask you things about the first semester again. I won't be asking you what encapsulation means or what static and private means, all that stuff. Okay. Excellent. Is there anything else you want to know? I know you want to know something. I can see it. Oh, you don't.
Has the venue been finalized?
I had an email on Monday about exam venues, but that may be for next year. But I'll find out. I'll ask our secretary to find out and post it on the web, and I'll add the schedule for the demos. No, not tomorrow. I'll do it tonight. Before tonight. I may do it over lunch. But that's just a random assignment, so it's easy to generate. Okay, right. I'm going to stop now. I must stop now. Thanks, guys. On YouTube.